Okay. So because this it's the exam period in the college, so we need to provide the online classes only during the exam period. So actually, and then unfortunately we had national holidays in the previous 2 classes. So I also recorded the lecture videos and then I posted the lecture videos. So I hope everyone already watched the recorded videos. Okay. So okay. So where is the this? So actually, I hope so we can conclude the memory hierarchy chapter in today's class. So okay. So I hope so. I believe everyone already watched the previous lecture videos. So and actually, so in the previous class, so I taught about the virtual memory. So this is the a little bit different topic in memory hierarchy. So and then I explained that the virtual memory was firstly invented due to the small sized main memory. Okay. So actually the first purpose, so first purpose of the virtual memory is actually it's the original purpose. The original purpose of a virtual memory is that so we want to use this small sized main memory like a cache, right? And then, you know, the size of the hard disk drive, the storage systems, so it's relatively larger than the size of the main memory. Also, how about the cost? The cost is cheaper, right? The cost is lower. So which means that the the price of the hard disk drive is lower than the price of the main memory per some size. So and then I also explained that in an old computer system, the size of the main memory was it's less than 1 megabyte, like the 640 kilobyte. It's so small. So it was very difficult to run applications on this small sized main memory. So we want to use we wanted to use the large space of the storage device for some space for the memory or application, and then we want to use we wanted to use this main memory like a cache. Okay, so the size of the virtual memory space. So why is it so big recently? So I will annotate, and then here see, right? I don't know why. So I think my app on the tablet is updated. So that's why it's not working well. What happened? Okay. But so the size of the virtual memory space is larger than the size of the physical memory. So actually, you will frequently hear about the terminology virtual or physical in other computer engineering courses. Or actually, it's the computer systems. Okay, computer system related courses, something like the computer architecture, also the operating systems, or compilers. Okay, so virtual. So terminology, the virtual means actually fake. It's a fantasy. also, and then the physical means that it's real, okay? So actually the virtual memory space, the size of the virtual memory space is larger than the size of real physical memory space. Because, so why? It is because we use the virtual memory concept to use this small size, the main memory like a cache. Then we want to use the large space in storage devices like some memory space, okay? So the virtual memory space, the size of the virtual memory space is larger than the size of the physical memory space, but obviously. And then modern computer systems, actually the modern computer systems equip this large main memory, right? The large DRAMs. So, but we currently use virtual memory concept because I explained that the software engineers, so actually when the software is designed, the software engineers cannot figure out the environment. So environment for software execution. So actually the hardware resources and then some environments like the number of processes or number of cores are managed by operating system. So when a software is designed, the software engineer assume that the target computer system has large memory, very large memory, okay? And then also the target computer system has enough computing cores, enough number of computing cores, okay? So actually we don't consider some hardware resources of the computer system when we design software, okay? Because so I frequently say that software engineers are playing in the fantasy world, because not real world. But the hardware engineers, actually the hardware engineers design the real hardware, real physical hardware. So we are playing in the real world, okay? So the software, actually the operating system or hardware just provide the virtual memory space, okay? So this is very large, and then also the software software does not consider about some memory spaces in the main memory. So it means that, so actually, computer systems, many processes are running. So you can check the running processes by clicking Ctrl-Alt-Del on Windows operating system, or you can execute TOP program on Linux. So actually, the many applications share the main memory, but so which means that the main memory space should be assigned to running processes. So, but software. So, and then when the software is designed, then software think that, oh, we can access this large memory only this one software. So, okay, so software, when the software engineers assume that when this software is executed, then only this software is running, and then this software used a very large memory. Okay, so but actual environment in the actual computer systems, many processes are sharing this physical main memory. So actually the storage space, so it's a memory space in the physical memory should be assigned to this many running processes, okay? So this virtual memory space, so actually this virtual memory space, so is mapped to this physical memory space, okay? So why is it so sick? But this translation is supported by operating system and hardware, okay? So this is the virtual memory concept. So software access the data with the virtual address, okay? So which means that the software think that, oh, we are accessing very large memory, and then only this one software is running on the computer system. So this is the virtual memory space, and then software access the data with the virtual address. But in a real environment, the request data is stored in the real physical memory, right? So which means that we need to access this data with the real address, which is the physical address, right? So this virtual address needs to be translated into the physical address, right? So the hardware, so the operating system supports this translation. And then in order to support this virtual address to the physical address translation, then operating system provides the page table. So page table provides this virtual page number, VPN, information, so translate the VPN to the physical page number called the PPN. And then actually this translation is performed at a granularity of page, right? So actually we handle the fixed sized page. So which means that actually this translation is performed at a granularity of fixed size like the 4 kilobyte, okay, 4 kilobyte of page. So which means that our data like the A variable A, B, C, blah, 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 these are included in the one page, okay? And then this virtual page number of a page is translated in the physical page number. But this because the size of the page is 4 kilobyte, many variables, actually this large amount of data, like the 4 kilobyte of data, can be included in the page. So the address inside of a page is called the page offset. Actually, this page offset is directly copied to the page offset of the physical address. Okay. So we only translate the virtual page number to the physical page number. And then in order to support this translation, the operating system provides the data structure called page table. Okay. So what happened? I don't know why this program runs ridiculously. So page table. So I said that this is a data structure like the page table and index. Okay, and then this index becomes the virtual page number, right? And then each element of this page table, and each element of this page table stores physical page number and other control bits, right? So actually this and the virtual page is virtual page number is translated in the physical page number. Then each page also has its own attribute, so like some properties. So these properties are also stored in each page table entry. Okay, like it's valid bit. Also, we can find the dirty bit. Also, we can find the permission bits like read write permissions. Also, we can find the protection bits, something like that. So we can find many control bits in the page table entry. So in each entry of the page table, that we can find the physical page number and some control bits. Okay. So, so when the load instruction is executed, so I'm leaving the previous class and what I'm leaving what we learned in the previous class, right? So when the load instruction is executed like the load A, so A is the address, and this address is actually virtual address, okay? And then this address need to be translated into the physical address in order to access the data in main memory, right? So this is the address, the virtual address, and then let us assume that the size of a single page is 4 kilobytes. So page offset occupies the lower 12 bits of the virtual address. Then, so in this example, the virtual address size is the 48 bits. So we need to translate the 36 bits of a virtual page number, right? So this is the virtual page number called the VPN. And then with the VPN, then we, in order to get some physical page number, which is mapped to this VPN, then we need to access the page table. So then I said that page table is a software data structure, okay? And then this page tables is managed by operating system, not hardware, okay? Hardware supports some page table access. Also hardware supports the caching of the page table called the TLB. But this page table is managed by operating system, okay? So, which means that the page table has the base address, it's a pointer of the page table. And then this pointer is stored in the page table register. And then we can access the first entry of the page table without this page table register. And then with the VPN, then we can calculate the offset for this page table, right? Then we can access the PT, so called the page table, and then VPN, okay? So when we access this page table entry, then we can get the VPN, and then with this VPN is concatenated with the page offset, then the physical address is generated, okay? Okay, it's better. Well, I said that but you know, this page table is stored in the main memory, so which means that in order to perform the translation from virtual address to the physical address, then we need to access main memory, right? So think like this. So this is the load instruction. Oh, what happened? Okay. I don't know why. So let us assume that we are executing load instruction. Load, oh, it's working. Load x1, 0, x2, right? So, and then I said that this address is the virtual address. And then in order to access the data requested by this load instruction, this virtual address need to be translated into the physical address. And then for this translation, then we need to access the page table with the virtual page number. And then, you know, this is the data structure. It's a software, right? It's just a software. So for this translation, we need to access the PT and then with the VPN. And then when this ppn is read from this target entry of the page table, then we can get the physical address of this load instruction. And then with this physical address, we need to access the memory hierarchy. Okay. So for this translation, then we need to access this data structure called the page table. And then, this page table is in main memory. So which means that when this load instruction is executed, and then for virtual address to physical address translation, then we need to access the main memory. And then I said that in the first class of the memory hierarchy chapter, I said that the main memory is so slow. So like so latency to the main memory is about 100 cycles, or even it can be 1,000 cycles. It's so slow. So we use cache to reduce the memory accesses, right? Because the memory is very, very slow. Okay, so we use the cache before this main memory. But ridiculous thing is that for this virtual address to physical address translation, then we need to access main memory. Okay. So even though this processor has cache, then we first access the main memory in order to get the information from the page table, and then we can get the physical address, and then with this physical address, then we can access cache. So which means that for this translation, we require 100 to 1,000 cycles to access page table in main memory. This is ridiculous, right? So because of the virtual memory concept, then the performance for the computer system will be degraded. Okay. So how can we solve this issue? Actually simple, right? So in the first class of the this memory hierarchy, why do you use cache? So what is the purpose of cache? Think about the cache. Why can we use cache? Because in our normal applications, strong data locality is observed. Then how about this page table? I said that the single page size is the 4 kilobyte. And then because of the data locality, then we can assume that our software will, if the software accesses a certain data in the 4 kilobyte of page, something like this, then with high probability, this same software will access the neighbor data, right? And then the size of the page, a single page is relatively large compared to the size of data requested by load instruction, right? So actually we execute this load double word. The size of the data requested by this load instruction is 8 byte, right? And then compared to the 4 kilobyte, 8 byte is very, very small. And then we assume that if this data is requested by load instruction, and then with a high probability because of spatial locality of the data, then we can expect that the same software will access the neighbor data, and which can be included in the same page. Do you understand? Because the data has exhibit the very strong spatial locality. When a certain data in a page table, in a page is accessed, then with a high probability, the same software will access the neighbor data, which are included in the same page. So which means that when this PT VPN is requested with a very high probability, the same page table entry will be requested again and again. Do you understand? Right. So we can apply the concept of cache to the page table. So what does that mean? Which means that, when the PT VPN is firstly requested, and then this data. So what is the data of this PT VPN? So data is the PPN and the other control bits, right? So we can get PPN and control bits. And then if this data is stored in a cache, then if this cache is located near the processor, so like the processor core, then we can access this data very quickly again and again. Do you understand? And then this cache, actually the processor supports the cache of the page table. And then this cache of page table is called the TLB. And then TLB means here is the TLB. Oh, okay. Actually, TLB is means the translation Lookaside buffer. So it is the TLB. And then actually this TLB is the cache of page table. Okay. So access to page table has good locality, as I explained. And then in order to use this locality, then the processor has a special cache for the page table called TLB. Okay. And then miss rate, this miss rate for TLB is very, very low, because so the page size is large compared to the size of data requested by load instruction. So the TLB miss rate is very low. So TLB is the good idea, right? Then how can we use the TLB? So how can we organize the TLB? So when I explain about the TLB, so think like this. So TLB is the cache of page table. And then in the real cache, why do you use cache? We use cache in order to get the request data quickly and requested by load or store instructions. Okay. So then how can you get a data? Cache, address is given. Address is given to the cache. Then we can get data. Then TLB. TLB is also a cache of the page table. Then which is given. What is the input of the TLB? So even though this is the only online lecture, interaction is important. So what will be given? So in a cache, the address is given to the cache, then we can get data. Yeah, right, VPN. So in a TLB, VPN is given because when we access the page table, then we access the page table with the VPN. So VPN is given, and then we can get VPN and some other control bits. Okay. Okay. So for cache, we can access cache with the address. And then for TLB, we can access TLB with the VPN, the virtual page number. And then this is the cache. So when the address is given to a normal cache, okay, and then address is split into the block of set, index part, and then tag part in a normal cache, right? And it's the same to the TLB. In the TLB, we provide the VPN to access the VPN. So this is the VPN, okay? So VPN. And then we can use the part of VPN as the index of the TLB, and then we can use the remaining part of the VPN as the tag of the TLB. It's the same to cache, right? So for example, if a TLB has how about 64 set, it's a set, okay? Then what is the size of the index part? It's 6 bits, right? Oh, I think it's, oh. So I said, so let us assume that TLB has 64 sets, like cache, okay? Cache can, so and then we can access the set of the TLB with the index part. And then what is the size of the index? It's the 6-bit, right? Is 2 to 6 is the 64, right? So among this VPN, the lower part, we can use the lower part of the VPN as the index of the TLB. Also, we store the tag part in the tag of the TLB entry. Okay. So if we compare with the cache, then so as I explained, then other VPN is similar to the address of cache, and then we can get VPN and then control bits, and then this is the data. So, and then in the VPN, so we use the upper part as the tag of the TLB, and then we can use this lower part as the index of the TLB, as the TLB is the cache, right? So this is the virtual page number. Then we can access the TLB with the virtual page number, okay? And then when we access the virtual page number, then we can get the index from this virtual page number. And then with this set index number, we can access the TLB, okay? Then the tag is read from this TLB of a target index, a target set. Then this tag is compared with the tag part of the VPN. It's same to the cache, right? And then if this tag is equivalent to the tag part of the VPN, so which means that TLB has the requested virtual page number to physical page number translation information, right? So mapping data. So in a TLB, we can get the VPN and some other required control bits. So This is the TLB hit. So like a cache hit, so an address is given to cache, and then if a request data is found, then we can check that if the request data exists in cache or not with address, okay? By checking tag of the address and then compare this tag with the tag stored in a cache. It's the same to TLB. TLB is also cache for page table. So BPN is given to a TLB, and then this BPN, you can split the BPN as the tag part and the index part. So which means that we access the TLB entry with this index number, and then TLB also stores the tag, and then we also compare the tag with the tag part of the BPN. And then if this tag is the same to the tag part of the BPN, then this is the TLB hit, which means that TLB has the requested mapping information from BPN to the PPN. So this is the TLB hit. So in this case, we can get PPN from the TLB. So we can get this physical page number very quickly. Understand? I hope you can understand. And then what is the TLB miss? So simple. So requested virtual page number is not found. So which means that we can access this TLB with the index part of the BPN. And then when the tag is checked, then this tag is not equivalent to the tag of the BPN. So in this case, this is the TLB miss, which means that this TLB does not have requested mapping information. Okay. So in this case, we need to access page table in main memory. Okay. So TLB hit, then we can get PPN from TLB, and then for the TLB miss, we need to access page table. So we can access the page table, but when the page table is accessed, then the requested page can be found in the main memory. So which means it is because the size of the virtual memory space is larger than the size of the physical memory space. And then actually you need to remember the original purpose of this virtual memory concept. So we want to use the physical memory like a cache. Okay. So which means that the requested page can be found in a main memory, or request page may exist in hard disk drive. Okay. So when the TLB is missed, then we need to access the page table. And then if this mapping information is valid and then it's found in this page table, then we can get PPN, and then which means that this page exists in the physical memory. And then if this PPN is not found, like this is invalid, so we can access some page table entry with the PPN, but it's invalid, so which means that this page table entry does not have any valid physical address. Okay, so in this case, we need to access the disk storage, like the hard disk drive or SSD, so solid state drive. And then this event is called the page fault. And then I explained that when we access a disk, like a storage devices, it's very, very slow, right? So when the page fault is encountered, then we need to access actually we need to access hard disk drive, and then we need to transfer the page block in a hard disk drive to the main memory, so physical memory, and then we need to also update the page table because the requested page is transferred from disk to the main memory, right? So this is very, very slow. So this is performed by operating system, not hardware. And then, so page fault is, I said that the page fault is the kind of an exception. Okay. So which means that when the load instruction is executed, then this load instruction may encounter page fault. And if the page fault is detected, so it means that the page table does not have any valid data. So exception is raised, the exception is detected, and then this exception should be handled by exception handler. So which means that this load instruction is canceled. Like, so I already explained how the exception is handled in a processor, right? So when the exception is detected, then the current is instruction that causes the exception is canceled, right? It's flushed. And then we need to jump to the address of the exception handler. Then the codes, software codes in the exception handler are executed by a processor. And then we need to return to the load instruction. So which means that when the page table is encountered, if the page table is detected, then the handler is executed. So the handler read the page from the storage, and then this page is transferred to the main memory, and then so this page table is updated. Okay, so it becomes the 1, and then this ppn is point to the location of the main, is the address of the main memory. Okay, and then this load instruction is re-executed, right? So in this case, then the load instruction will access the TLB and the page table, but now we can find the valid mapping information from this virtual page number because the request page which was in the disk storage were transferred to the main memory, right? Understand? So I explain about actually this how this TLB misses or some page table misses are handled in operating system or hardware. Okay. So let's see this slide. So it's a TLB miss. So in the TLB miss, and I already explained that. So TLB miss means that so requested mapping information is not found in TLB, then we need to access the page table. Okay. Then if the page table has a valid mapping information, then it's a cache. So which means that this valid information is transferred to the TLB, right? It's like a cache miss. So when the cache is accessed, the cache is request. So when the load instruction requests data from cache, and if this request data is not found in a cache, then we need to access the low-level cache or main memory. It's the same to the TLB. When the TLB is encountered, then we need to access page table. Then if the page table has a valid data, then this data is transferred to the TLB. Okay. So this TLB misses can be performed by hardware or software. Okay. So it is determined by some hardware support or need this TLB miss can be handled by software only, like the page fault exception. So which means that when the TLB miss is encountered, then the software, so actually operating system has the software calls, handler for the TLB misses, then this TLB miss code can be executed. Or so this TLB miss can be handled by hardware, okay? And then it's called, actually every processor has the memory management unit called the MMU, and then usually these TLB misses are handled by this MMU, so memory management unit, okay? And then in the TLB miss case, and then this target page is not found in a page table, then it's the page fault. This is the exception. And then this page fault is handled by software operating system, okay? Okay, so I already explained here. Then let's see how the TLB interact with cache. Okay, so first in chapter 2 or chapter 4, we assume that when the load instruction is executed, so load A, this is the address, then we assume that then we can access the main memory with this load instruction. And then in chapter 5, so we learned about the memory hierarchy. Then we learned that actually this load instruction access cache, not main memory, with this address, okay? But we realized that, oh, it was a virtual address, not so. And then this address is not real address, okay? Then, so which means that we learned that, oh, this virtual address need to be translated into the physical address, okay? And then actually, so cache is the part of memory hierarchy. Then, when the data is in this memory hierarchy, then we need to access data with the physical address, not virtual address. Do you understand? So which means that when the load A is executed, then cache. How about the cache? Cache needs to be accessed by physical address. Do you understand? So actually, when the load instruction is executed, the load A, then this is the virtual address. This virtual address needs to be translated into the physical address of T. So this is the virtual address of A, and then this virtual address needs to be translated into the physical address of A. And then with this physical address, we need to access the cache. Okay. Then let's see how the TLB interact with cache. So this is the virtual address of load instruction. And then we need to access the TLB with the virtual page number, right? So we need to access the TLB with the virtual page number. And then, this page offset is not translated. We just access the TLB with this virtual page number. And then if we access this TLB, and then for the TLB hit case, then we can get physical page number. And then page offset is just copied and concatenated to the physical page number. So this is the physical address. Then this physical address is split into the index part of the cache, and then block offset, and then the tag part. And then we access this cache with this cache index. So we access cache or target cache set with this cache index. And then we check the tag in a cache with this physical address tag. Okay. And then if for the cache hit case, then we can get data from cache. So what is included? When we learned about the cache, we think that cache is accessed by processor. The load address of the load or store instruction directly. But it's not true, actually. Because of the virtual memory concept, this virtual address of load or store instructions need to be translated into physical address before accessing cache. Okay. So firstly, when a processor accesses a cache, so firstly we need to access the TLB, and then we can get physical address, and with this physical address, then we need to access the cache. Okay. But what's the problem? What's the problem with this process? Problem? Stop. Hit time. So I said that we thought that we can access cache directly with the address of the load instruction, but its assumption is not true. Actually, we need to access TLB first, and then we need to access cache. So which means that it's the two-step process, not one step. So which means that in order to access the cache, we first the cache access latency is added by the access latency of the TLB plus access latency to cache. Okay, so which means that hit time, the access latency will be increased. Okay, so this hit time is also critical for the performance of cache. So which means that when we calculate the AMAT, the average memory access time, then average memory access time is the hit time plus miss penalty multiplied miss rate, right? So hit time is also critical for the performance of cache, but because of the TLB, the hit time will be increased. So that's the problem. So instead of this, so which means actually the cache need to be accessed by physical address. But for the level on cache, some processors access level on cache with the virtual address. Do not reduce the hit time of the cache access latency, hit time of the cache accesses. Okay. But there can be actually this concept of virtual address access is also has a problem. So, but actually this is the somewhat advanced topic of this virtual memory. So I will not cover this problem. But so we need to remember that actually we need to access cache with the physical address, and in order to get this physical address, we first need to access TLB. Okay. But sometimes some processors can access cache with the virtual address, and then we need to handle some problems caused by this virtual address successes to cache. But so I will explain in this course. Okay. Okay. So also the virtual address can be used for memory protection. because so using the virtual memory concept, then the operating system can decide which physical memory access resources are assigned to which learning processes. So for example, this is the physical memory space, and then this part is assigned to the application A, and then this part is assigned to the application B. And then we actually operating system control this memory space assignment using page table. Okay, so which means that when an application is launched, so an application is executed, so we can execute an application by clicking icon of the application on the Windows, where we can directly execute the application with the command. Okay, so when an application is launched, then actually the operating system assign the page table to this launched application. So actually it's a page table A. And then when the application B is launched, operating system also assign the page table for this application B. Okay. So, and then based on these multiple page tables, then operating system allocate the physical memory space to different applications. So which means that this part is assigned to application A, so another part, the different part is assigned to application B. And then for some cases, the data can be shared by application A and B. So which means that so A and B can be shared by the same location of the physical memory can be shared by application A and B. So it's simple, right? So like the virtual address of this A and the virtual address of this B can be translated in the same physical address. Then the data, the physical memory space can be shared by different applications. Also, because in order to access this physical memory space, then we first need to translate the virtual address to the physical address, so which means that we need to access the TLB or page table for accessing main memory, right? So by assigning some specific control bits like a memory protection bit, then operating system also control the memory protection using this page table. So which means that this space is only assigned to the application A, and then other applications cannot access this part. So the protection bit is also assigned to the part of the page table entry. Okay, it is assigned as like some control bits of the page table entry. Okay, so operating system also can provide the memory protection function using this page table entry. Okay. So this is the end of this memory chapter, and then so before moving on the next topic, then I will show you the one. I will show you the pop quiz, pop quiz questions. Okay. Can you see pop quiz questions? I think it is working because I can see my avatar's screen. So this is the package. It's the last package actually. Last package of this this course. So you can access our Blackboard to answer questions on this package. I will resume the class at 3:04. So we have 2 minutes left. Okay, I think it's enough. So this is my right hand. Okay. Okay, so I will conclude this chapter 5 of the memory hierarchy and the memory system of the computer system. So we learned about the cache, also we learned about the virtual memory. So cache and virtual memory are the main topics in this memory hierarchy chapter, okay? And then, okay, so I will skip to this slide. So, and then let's see the cache organization example of a real processor. So this slide shows the example of cache configurations in ARM Cortex-A53 and the Intel Core i7. So this is rather some old i7, not the current i7. And you can find some different cache configurations in this table. So you can find the level 1 caches, and then level 2 caches here, and then level 3 caches. So Intel Core i7 is the multi-core architecture. So it's a CMP, chip multiprocessors. So, and then which means that this Intel Core i7 includes the multiple cores, and then actually the level 3 cache is the last level cache, and this is the shared cache. So also you can find the configurations here. So if we see the ARM Cortex-A53 for the level 1 cache, instruction cache and data cache are split. It's the same. The Core i7 instruction cache and data cache are split because not to avoid structure hazard, right? So in order to avoid the structure hazard, instruction cache and data caches are split. And you can find the cache size here. It's a six. You can configure the size of the level on cache of the ARM Cortex-A53 from 16 to 64 kilobyte, and then it's a 32 kilobyte. So usually the size of the level on cache is small. Then you can find the set associativity of cache, so 2A and 4A, 4A, 8A. Okay, so different configuration. How about the replacement policy? So random and then approximated RRU. So actually implementing the precise RRU is not easy. So it's somewhat complex. So we frequently use the approximated RRU or pseudo RRU. Okay. Now you can find the block size is 64 bytes. And then, so you can find the right policy here. Okay. Also for the L2 cache, L2 cache is the unified cache. I already explained it's a unified cache per core. So which means that Intel Core i7, the L2 cache is the private cache. So which means that L2 cache is not shared by other cores. Okay. You can find some size and set associativity, blah, blah, blah. And then also you can find the heat time. Okay. So 2 clocks and then it's a 4 clocks. Okay. And then also you can find the, oh, this cache is the pipeline. So actually the pipeline, the processor, that we assume that the heat time of the cache is 1 clock, but actually the heat time is the multiple clocks. Okay. Also, this is because in order to access the cache, then also the cache size is a little big, but also we need some processes to access cache. Okay, so that's why this heat time is multiple cycles. But you can find the heat time for L2 caches like 12 and then 10 cycles. And how about the L3? L3 is very large, and then also you can find that it's a shared cache. In the multi-core architecture, usually the L3 cache is the shared cache, as I explained. And then if you see the associativity in the level 3 cache, then it's the 16-way. The associativity is also high. I already explained. And then heat time is very low. It's because the level 3 cache is very large. Okay. And then how about the TLB? So if we just see the virtual memory address of the ARM Cortex-A53 and then the Core i7, then we can find that our virtual address is the 48 bits. Okay, then what is the size of virtual memory? Its size is the 2 to 48 byte, right? And then 240 is the tera. So 28 is the 256 terabyte. Okay. Also, actually, we learned about the 64-bit computer systems. So which means that when the load instruction is executed and when the load instruction calculate the address, and then we assume that this address is the 64-bit. Okay, so and then I said that this is the virtual address. But instead of this 64-bit, 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 we use the 48 bits. This is because if we use the entire 64-bit, the virtual memory size will be very, very large. So I cannot calculate. So 40 is the tera, and then I think the 50 is the peta. Then maybe. I don't remember. So it's very, very large, but actually, if the software handles this size of the data, it's not possible. So actually, our normal applications handle some it can handle large data, but the size of this data will be smaller than the 256 terabyte, right? We cannot imagine the 256 terabyte handled by a single software, right? So that's why instead of 64-bit, the most of processor supports the 48 bits of virtual address. 64-bit is too large. We cannot imagine of the data which have a 64-bit sized virtual memory space. Okay. And how about the physical address? The ARM is the 40-bit, and then this Intel Core i7 is the 44 bits. So actually, this physical address size determines the maximum size of physical memory. Okay. But actually, the size of the supported size of the DRAM is determined by hardware limitation, like a DRAM controllers. But the physical address is the maximum size of the memory space supported by virtual memory concept. And then how about the TLB? You can find so actually in this course we learned the page table is the 4 kilobyte, but sometimes we can use huge table. Okay, so which means that the single page size can be increased, like 4 megabyte. Also, you can find some organization of the TLB, and then I said that TLB is also the cache for page table. Then you can find some organization like here. So actually, for the add-on cache, the instruction cache and then data cache are split. So in the TLB, it's the same. So one TLB is assigned for instruction cache. So this TLB is called the ITLB. And then another TLB is assigned to the data cache. And then this TLB is called the DTLB. Okay. And then if you see this, so you can find that one TLB for instruction and one TLB for data. It's the same for Intel Core i7. So if we see the organization of the TLB, so if we see the Intel TLB, then add-on ITLB has 128 entries for small pages. And then so configuration is a little bit different. And then the TLB has the 64 entries. And if we see the L2 TLB, so TLB is also assigned to the L2 cache. So TLB is also hierarchy. So you can find, it's a 4-way set associative and then RRU replacement. Okay. And then L2 TLB has 12 entries. Because the TLB is a cache, TLB can be organized like a cache. So it means that TLB has also associativities like cache. So TLB also has some replacement policy. Okay, because this is the set associative TLB. Okay. Okay, so we will conclude. I will conclude this chapter. So we really want fast, large memory, but this is the ideal memory. So we live in a real world, not fantasy world. Okay, so because we cannot use ideal memory, so we use memory hierarchy, right? And then we can use the memory hierarchy because of locality in software, locality in data. So in this chapter, we learned about the cache and then virtual memory. So these are very important topics in memory systems. Okay. Okay. So this is the end of the chapter 5. And then any questions? Okay, thank you for your attention. And then the next class is the last regular class. Okay, and then in the next class, I will briefly cover the chapter 6 of the textbook. 출석은 뭐 공휴일은 어차피 출석을 할 수 없기 때문에 그냥 그거는 다 출석한 걸로 처리합니다. For the recorded lecture, actually I cannot check the attendance, real attendance, actually real watching, okay, for the lectured video. So actually for the previous 2 classes, I assume that everyone already watched the lecture video, so which means that everyone attended the previous 2 classes. Okay. Okay. Thank you for your attention, and then see you in the next class.